So we would like to discuss upper and lower limits. We're going to look at the case that is of most interest to us, but everything we say will be true for limits as x tends to any conceivable destination. But let's say that we look at the function f of x, which is defined from 0 to infinity. And we ask the question, actually, it could be defined for x large enough, so it doesn't have to be from 0 to infinity, it could be from 1000 to infinity. But the bottom line is that we're asking if the limit as x tends to infinity of f of x exists. And the answer is for a general function is, of course, not. For So, and we can give very, very simple examples. So take, for example, the limit as x tends to infinity of sine x, right? I mean, you can easily see that this function oscillates as x becomes larger and larger, and certainly it doesn't, its outputs do not approach any specific number. So this does not exist, as a very simple example. So the question is, can we replace the limit as x tends to infinity of this function by limits that do actually exist and give us some information about the behavior of the function? And the answer is that we have two limits, the so-called upper limit as x tends to infinity of f of x. So this is going to be called the upper limit. And sometimes it's also denoted by lim sup as x tends to positive infinity of f of x. And then we have the lower limit. And this is called the lower limit. And sometimes we also call this the lim inf as x tends to infinity of f of x. So we have this notation, and this can be defined as follows. So first of all, the truth is that we can always find sequences an, not just one, many, for n in n, with limit as n tends to infinity of an equal to infinity, and such that the limit as n tends to infinity of f of an exists. Okay, so let me give some very simple examples for this standard oscillating function that I mentioned, so sine x. So for sine x, for example, if we take this as a1, this as a2, this as a3, and so on, then the corresponding f of a1, f of a2, f of a3, they're all equal to 1. So certainly the limit of f of an exists. Or we could take, let's say, pi, 2 pi, 3 pi, 4 pi, and so on. And again, this is a sequence of points that tends to infinity, and limit of f of an exists, it's equal to 0. So certainly we can find such sequences whose limits do exist. Limits of the corresponding outputs of the functions do exist. And one can show that among all such limits of such possible sequences, there's always a largest one and the smallest one. So it can be shown that the set of all such limits, so L, such that there exists an tending to infinity with limit as n tends to infinity of f of an is equal to L. So for this, that this set has a smallest element and the largest element. And a largest element. And also note that positive infinity and negative infinity are allowed to be elements of this set. Okay. So in other words, for any function defined for all large enough real numbers, the upper limit and the lower limit always exist. So the limit may not exist, but these two limits always exist. And it turns out that we have the following important property. Again, none of these things is too hard to show. One can needs to proceed with basically the definition of limits, but we're not going to pursue the proofs. That limit as x tends to infinity of f of x exists if and only if the limit, the lower limit, is equal to the upper limit. Okay, so in general, of course, one should say that the lower limit, being the smallest element of that set, is always less than or equal to the upper limit. But basically, if the two limits are the same, then the limit of the function exists. So all of a sudden, we go from a situation where we can be considering a function whose limit may or may not exist to a situation where the limits do exist. And here we should also say that we have the following very simple property for such limits that we would like to mention. That if we happen to have two functions that one is less than or equal to the other, so if f of x is less than or equal to g of x for large enough x, doesn't even have to be for all the x's, for large enough x, then the limit as x tends to infinity of f of x, the lower limit of f of x of the smaller function is less than or equal to the lower limit of the larger function. And the upper limit of the lower function of the smaller function is less than or equal to the upper limit of the larger function. And actually we can give a very simple interpretation for this. So start, for example, with this inequality, and take the specific sequence that realizes this limit, right? So let an be such that limit of g of an as n tends to infinity is the lower limit. Then if you consider now f of an doesn't necessarily converge, but we certainly have that f of an is less than or equal to g of an. And I should say f of an doesn't necessarily have a limit, but there's a very interesting property of sequences that says that any sequence has a subsequence that has a limit. So f of an itself may not have a limit, but there is a subsequence, meaning an infinite choice of its terms, that does have a limit, and that limit has to be less than or equal to the limit of g of an. So there is a sequence that has a limit which is at least less than or equal to that of g for f, and that makes the lower limit of f of x less than or equal to the upper limit. Now, we could do a similar argument for the upper limits, but it would also be interesting to notice, and that will finish this very easily, that the lower limit, okay, let's make sure that we say this correctly now, the lower limit of the opposite of a function f of x is the opposite of the upper limit of f of x. So, and you can very easily see this by taking a function that, let's say, a function like sine of x. So you're looking at the smallest values that negative sine of x takes, okay, like these ones, for example. And these ones really correspond to the largest values that sine x takes that have been flipped. That's pretty much the idea behind this. So this tells you that if you have a property that holds for lower limits, then you can pretty much have a property that holds for upper limits. So here, if I wanted to take advantage of this in order to prove the corresponding statement for the upper limits, then I would take that if, oops, sorry about this, that if f of x is less than or equal to g of x, then negative f of x is greater than or equal to negative g of x. So now we can apply what we said about the lower limits here. So the lower limit as x tends to infinity of negative f of x is greater than or equal to the lower limit as x tends to positive infinity of negative g of x. Yes, but now the left-hand side is nothing but the opposite of the upper limit of f of x, and this has to be greater than or equal to minus the upper limit of g of x. And of course, now you multiply both sides by -1, and you get what we had suggested to begin with. So that tells you that pretty much there is a duality, as we say in mathematics, between upper limits and lower limits. Whenever you give a statement about upper limits, that has a counterpart for lower limits and vice versa. So in any case, these are the interesting things that we have about the case where one cannot assert the existence of a limit, which means, for example, that in the case of the prime number theorem, where one wants to find the limit of the amount of prime numbers that do not exceed x over log x, and a priori one doesn't know, from the beginning one doesn't know if this limit exists, one can start talking about the upper and the lower limits. And that's all that we wanted to say about upper and lower limits. Thanks for watching.